All right. So I did, Lauren pointed out here um, on the previous recording when we came up with our fancy little formula for finding the average rate of change between the point 1 comma 2 and another point that's x value h units away for the curve 3x minus x squared. I meant to say that h can't be 0 right there, right? H can't be 0. And I put an equal sign. Because again, when h is 0, we're back to just a single point. So notice that little formula that we did, 1 minus h, did give us all of the different values here. And just to be thorough, I guess, on this last one, part D, we went from 1 to 0.001. So h was 0.001. And of course, then the average rate of change, when we're that far away, ended up being 1 minus 0.001, which was 0.999. So, you know, I think the moral of this story is, even if we're not trying to invent calculus, a little work, you know, on the front end can save a lot of work. On the back end? No, maybe that's not what I want to say. Sometimes there's a better way to do things, right? And notice it's super easy to do 1 minus the number rather than, I mean, just think if we evaluated part D by hand, f of 1.001. I'd have to plug that into the function 3 times 1.001 minus 1.001 squared. That's kind of like, that would be hard without a calculator, but really, the final answer would have just been 1 minus that number. Much easier. It's clever how that works out. Now, here's kind of we could do. Look at part C. Now that we've called this little fancy formula, and I did call it a of h, thanks again, Landon, I could take the limit as h goes to 0. Let's try that. That would be the limit as h goes to 0 of a of h, which of course is 1 minus h. And by direct substitution, we get 1 minus 0, which is what? 1. Now, again, remember, when I plug in a 0 there to evaluate the limit, we know that we're not claiming that h is 0, are we? We have already divided out the 0 over 0. And we know algebraically that the function a of h up here, before we divided out the h over h, we know that that function has a hole at h equals 0. And we know how to find the y value of the hole without actually going into the hole and falling through it. That's what we did in 1.4. So that's where the limit is so important, because it allows us to get answers without having to go there. So I think we can actually say now, by computing, that yes, the slope of the tangent line is in fact 1. That graph at that moment, the point 1 comma 2, is going up 1 unit for every one it's going to the right. And it's decreasing, right? Because as we go to the right, it's flattening out. That's something else. That's second derivative. We'll talk about that later. All right, so now example 3. I think we're ready to kind of go abstract here. One more step. So in the previous step, we didn't define the second point as a specific point. We said it was h units away. Now what we're going to do is the same idea, but we're not going to pin ourselves down anymore at the point 1 comma 2. Okay, we're going to call the point 1 comma 2. Let's go ahead and just say this. Let's call the point 1 comma 2, which is really, you know, 1 comma f of 1. Let's call it x comma f of x, right? No, in other words, let's treat x as a constant. Let's just pretend that the symbol that we use to write the number 1 is x. And let's pretend for a second that we misspell the number 2 as f of x. You know what I mean? Let's just physically go through and replace this symbol with this symbol. And we'll replace this symbol with this symbol. And we'll work it the same way. We'll just pretend that x is a constant. So here we go. We'll say then that the average rate of change now between our constant point, our specific point, wink, wink, right? X comma f of x, wink, wink, and a point that is h units away horizontally, x plus h, f of x plus h. So here we go. The average rate of change, I'm just going to call it a. You can call it m for slope too. It's f of x plus h minus f of x all over x plus h minus x. Change in y over change in x. It's still just a difference quotient. And of course, we can simplify the denominator. The denominator simplifies to x minus x, goes away, and we're just left with h, which again is not surprising. This is still your delta y over delta x. And we're using h for delta x. This is actually looking more like my favorite problem from pre-cal because the second term is not a number. Or is it? We're treating it like a number, right? Wink, wink. F of x is just some constant. All right, now let's plug it into our function, which says 3 input. Remember, f of input is 3 input minus input squared. All right, so if I set up the first term in the top, again, I'll use grouping symbols here. It's going to be 3 input minus input squared. And that's going to be x plus h, x plus h. And then I go to the next one. I'll use grouping symbols again. Minus f of x, which is just 3 input minus input squared. And all that is over h. This is my favorite problem. In fact, that's very similar to what the last question on the pre-cal exam was. But to them, they were just setting it up and evaluating it. To us, it's the average rate of change between the point x f of x and a point h units away. Now if I distribute, I get 3x plus 3h, square multiply double square, and distribute the negative, yes? Minus x squared, multiplying double gives me 2xh, distributing the negative, I get minus 2xh, square h, I get h squared, and distribute the negative, I get minus h squared. I'm going to change this to red. Probably should have kept that. There we go. So that matches up with that first term. And then minus, we just distribute the negative, minus 3x plus x squared all over h. So this is just sledgehammering it, right? Careful expansion. Keeping the equal sign down the left side because we already started it as a equals, and make sure it's still all over x. Now here's your checkpoint. Somebody in pre-cal said we should divide or cross things out or divide things out with a highlighter. I like that. Everything without an h should cancel. 3x minus 3x, that's gone. Plus x squared minus x squared. And then the 3 terms that are left, which I'm not going to highlight because it'll get in the way. Let me just go ahead and write it. 3h minus 2xh minus h squared. That's what's left. And again, notice, we still can't let h be 0. If h is 0, we're back to the tangent line problem. When h is 0, we're using only one point. When h is 0, the algebra doesn't work. It's safeguarding itself against using 0. And we're like, nice try, algebra. This function right here, a of h, we know it has a hole at h equals 0 because it gives us 0 over 0. We've spent most of the first 3 weeks figuring out algebraic remedies for that. Yeah. So this is no exception. We are going to do the same thing. We're going to factor out the h, and that gives us 3 minus 2x minus h squared all over h. It divides out. And minus, yeah, there you go. There we go. Took an h out. And we get a of h is equal to 3 minus 2x minus h. Now notice, we've been treating x as a constant this entire time. And if I let x equal 1, which is where we started the whole problem, right? When x equals 1, you end up with 3 minus 2, which is 1. You end up with 1 minus h, which is the formula we had right before lunch. But what we've done now is, since we kept x all the way through to the distilled product, I can say that now x, you're allowed to You're allowed to be free now. Go X, be anything you want to be. You're no longer supposed to be a 1. You could be a 0 or a 5 or anything. And so what I've now created is a formula that allows me to find the average rate of change. This is of H and X. This is 2 variables, how you write it. Now I can pick any X I want and any H that's that far away from it, and I can get the slope of the secant line between those 2 points, okay? I mean, it's pretty nifty. So for instance, if I wanted to figure out, you know, the average rate of change, let's just say from 2 to 3 right there, this would be that line. I'm not going to actually calculate it, but this would be X equals 2 and H would equal 1, right? If I want to find the slope of this green line, well, let's go ahead and do it. I think I remember what it was. A of Hx is 3 minus 2x minus H. Yeah. And so let's see what the slope of this line is. I don't have to compute anything other than know the X value that I want and how far away, 1 point away. So this becomes A of 1 comma 2, which would be 3 minus 2 times 2 is 4 minus 1, and I get negative 2. So there you go. Apparently the slope of this line is negative 2. That function on average falls 2 units as this graph spans from 2 to 3 for every one it goes to the right. Nice to know. It's a broader equation that I can use all over the place, okay? All over the place. But it's still just an average rate of change. It's still just the slope of a secant line. Bummer. What if I wanted to know what the slope of the tangent line was at 3? If I wanted to know exactly at this moment how fast the function was changing. Not the average from 2 to 3, but how fast it was going down at 3. Well, that brings us to kind of the next progression. Let's take this right here, and let's take the limit. Let me leave a little space here. Leave a little space in front. What would be the limit as, again, H goes to 0? I can use direct substitution, and I get 3 minus 2x. And again, when I plug in a 0 to evaluate that, I know I'm not claiming that H is 0. Don't make that claim, because if I do, then I'm doing algebra. But I know algebraically that I can cleverly find the y value of the whole, which is 3 minus 2x. And again, we treat x like a constant until we get to the end. And once we get to the distilled product, I can say x, you can float and be free and be whatever you want. That right there is now a function of x, isn't it? And because h went to 0, this gives me a formula for finding the slope of the tangent line at any value of x. We're going to call this now not the slope of the tangent line of x. I'm going to call it f prime of x. That's what that little mark means, f prime of x. I use the same letter f as the original function. That function f gave me y values. I'm going to put f prime to show that it's still related to f, but different. F prime of x is nothing more than a function now in terms of x that allows you to find the slope of the tangent line at that value of x. It's the instantaneous rate of change of the function. We did it. We not only circumvented it at the point 1, 2, only having 1 point, we found a formula that allows us to find the slope of that graph at any point. Wow. Let's verify it. We snuck up on this slope here, right? We said that the slope of that tangent line was 1, didn't we? That's what all this work was, right? It was approaching 1. Well, let's see. If I use my new formula, that's just finding the slope of the tangent line when x is 1. That would be f prime, we call it, of 1. That gives us 3 minus 2 times 1. Oh my goodness. That is, in fact, 1. Remember over here, I was just kind of curious and I wanted to find out the slope at 3, how fast this function is going down at 3. It's going down pretty fast. When x is 3, at that instant, how fast is the graph going down? Well, that's f prime of 3. That's going to be, according to my equation, which, I can let x be a variable again, 3 minus 2 times 3. That's 3 minus 6. That's -3. That's reasonable because it's steeper than it was at 1, but it's negative. So it's going down 3 units for every one it's going to the right. At that instant, at that moment, oh boy, that's powerful. We just invented calculus, and we never divided by 0. Now, you can use this handy-dandy formula a different way. Instead of inserting an x value to figure what the slope is there, if you know what you want your slope to be, you can set it equal to that slope and solve for x, right? Just like you can with any formula. Plug in an x, find an output, set it equal to the output, solve and find the input. Watch this. We said way back in the beginning that the vertex was at 1.5, okay? The vertex of a parabola is always at the average of your x-intercepts because a parabola has symmetry, but cubic polynomials don't. Fourth degree polynomials don't. So look what we could do. If I wanted to know the x value of the vertex, what do we know about the tangent line at the vertex? What does it look like? It's a horizontal line, and the slope is 0. So let me see if I can draw that. There you go. Oh, that's not horizontal. I can do better. I can do better. Yes, I can. There we go. I know that the slope is 0. This is the power of calculus, because this not now only solves the tangent line problem. If you remember, I told you in the beginning, one of the other problems they were trying to solve was the max-min problem. What is the input value, the x value, that maximizes this curve? How many items do I produce to maximize my profit? The absolute maximum here occurs at the vertex, which is when the tangent line is 0. So look, I come back all the way down here to my little formula, and instead of plugging in an x, I'll just say f prime of x equals 0. I set the whole thing equal to 0, which is really when 3 minus 2x equals 0, right? Solve it algebraically. And then, of course, that becomes 3 equals 2x, and x equals 3/2, which is the same as 1.5. Oh my gosh. So now, we don't need to do this for parabolas because we can find vertices 2 other ways. We can average the x-intercepts, or we can use the first part of the quadratic formula, negative b over 2a. But now I have a more general method. If I can find the derivative, as it's being called, or will be called, let's give this a name. This is going to be known as the derivative function. We derived it, didn't we? We derived it cleverly using the rules of algebra, but we did it standing on the foundation of our house of calculus. This is going to be known as the derivative function. The derivative function will give us a function of x that gives us the instantaneous rate of change of that curve at that x value. That also gives us the slope of the tangent line at that value. So if I ever want to find a vertex or a local max or a local min of a cubic polynomial or something that's not a parabola, I can't just use symmetry because there isn't any. I can use this. I can find the derivative somehow using the same method that we just did, set it equal to 0, solve for x, and I'll have possible location. That's fantastic, okay? If you listen closely, you can hear Galileo grumbling in his grave. Grumbling in his grave. You know why? We just did, in the time after lunch, during C lunch, we just did what he kind of was trying to accomplish his entire lifetime. He could only come up with average rates of change of those balls down inclined planes. And he came up with pretty good accurate, but he never was able to make that leap from, empirical work to theoretical work, where it's now just, here's an explicit equation. You want to know how fast that ball is rolling down that inclined plane at t equals 2 seconds? Just plug a 2 in to this equation and you have its speed at that moment. He was never able to do that. And we just did. Galileo's grumbling, grumble, grumble, grumble. He's proud of you, though. He's happy. He's fortunate that at least we've made progress. Wait, that was just his stomach grumbling after lunch. I'm sorry.
Sorry about that.
Yeah, it's okay. Yeah. Don't get a tummy ache from too many sweets. The slope function that we found, have all you want though. The slope function we found in the previous example is again called the derivative function of f of x. Okay? We denote it as f prime, that's how it's read, f prime of x. And of course, it can be used to find the slope of the tangent line at a point or the instantaneous rate of change. Wow. Now, remember what we did up here was kind of general. I was still using function notation up here, right? After I canceled out the x's and I just put it over h. So at this point, this could be applied to any function, right? I only made it specific on this bottom line here when I plugged it into 3x minus x squared. So if we can take this right here, which is my favorite problem, and instead of algebraically working around the 0 over 0 problem at the end, let's go ahead and stick the limit in front of it to begin with. The limit as h goes to 0. If I can do that, that'll take this average rate of change, slope of the secant line, it'll take it magically to the next level and turn it into an instantaneous rate of change or a slope of a tangent line. And that's the limit definition of the derivative. Muy, muy importante. Okay? If f is a differentiable function, now what does it mean for a function to be differentiable? Good question. A function, it says up here, a function that has a derivative at a point is said to be differentiable. We'll explore that a little bit more later. Okay? There are some visual cues that you can use on the graph or the equation to determine where a function is differentiable. But for right now, just real simplistically, if a tangent line slope exists there, we'll say it's differentiable. If a derivative exists at a point, it's differentiable. So if f of x is a differentiable function, then its derivative, f prime, is defined to be this. So you need to know this, you need to commit it to memory, but you know what? You don't have to memorize it because you already know it, don't you? I took the entire period after voting for Cade Wenzel to come up with that, so that I nursed you along from something that's completely concrete and finite to now something that's abstract and can be used theoretically for any function, okay? It's the difference quotient, the change in y's, over the change in x, which we use h instead as h goes to 0. You may see this in other textbooks, you know, if you get to a professor who's old and cantankerous, some old timers still, you know, cling to using delta x as a single variable, which is fine. Okay, so if you replace h with delta x, it's the exact same thing. But we like h nowadays because it's a single letter. But it's equal to f prime. Okay, and you can now find a derivative function, as we call it, for any function that's differentiable if you set up and evaluate this limit definition. Okay, there are other notations for f prime. If it's not in function notation, you could just casually call it y prime. So if it's y equals, that's the function. Y prime would be its derivative. Okay, now here's the one that I really like. We call that differential form, which is really Leibniz form. If you remember, I said that Newton kind of gets the credit, but Leibniz has the last laugh, if there's any to have, because we use Leibniz notation. And dy over dx is Leibniz notation. We'll study these again later, but dy is called the differential of y, and dx is called the differential of x. Now, the reason I like that is because, one, it pays a shout out to Leibniz. I kind of like Leibniz. Number two, it preserves the quotient feel of the derivative, right? because we are finding a rate of change, how fast something changes with respect to something else. It's a quotient. So Leibniz notation is a constant reminder that finding slope or finding derivatives or finding instantaneous rate of changes is a division process. It's division, okay? The other reason I like it is because it does have that analogous feel to the average rate of change, right? What you're used to. In Algebra 1, we've written it several times today. We abbreviate the difference quotient, delta y, change in y, over delta x. So Leibniz notation is very similar. Now here's the difference. Delta y is a finite measurable vertical distance. That's what delta y is, finite and measurable. dy, the differential of y, according to Leibniz, is an infinitesimally small, non-measurable change in vertical distance. And it goes the same with delta x. Delta x is a finite measurable horizontal distance. Even if it's small, it's still finite and measurable. And dx, the differential of x, is infinitesimally small, non-measurable. And so that's how Leibniz kind of avoids division by zero. He's saying that the ratio dy to dx was kind of like what we were doing up at the top when we did f of 1 and f of 1.00001. Just imagine putting like as many zeros as you can tolerate. X equals 1 and 1.1. That distance between them is so small, you can't measure it. So Newton's, or Leibniz's kind of method has the seeds of limit notation in it. Leibniz never wanted to divide by zero. He said it's just so small, the writing's on the wall, you could see it. Newton, on the other hand, just went, I'm dividing by zero. Like it or not, take it or leave it. I'm Newton. And he did. Okay? So there's only two people in the history of the world I know of that have ever divided by zero and gotten away with it. Of course, Isaac Newton, and he did his by guile and intellect, and then Chuck Norris, who just does it by brute force. Yeah. I'll have to show you how Newton divided by zero tomorrow, if you remind me. Bring your safety goggles, just in case something happens when we divide by zero, because it's not really safe. Be working on your worksheet, and oh, by the way, we probably should quiz tomorrow over the IVT, okay? Keep voting though. Have a splendid, super duper awesome rest of your day.